Okay, so we are going to start a new concept today. Well, maybe new to Troy, and maybe not so new to the rest of you. So we're going to start looking at friction. Okay, we've, for the most part, either been given, we've made some very big assumptions about friction leading up to this. Right now, we're actually going to look at how friction works in motion. Okay? So one of the biggest things when we consider friction is we need to remember that friction changes, right, in order to prevent motion. Right? It's a resistance force. It usually acts in the opposite direction to the direction of the force, not always, but it generally acts against the direction of motion, okay? Generally. So if we consider something simple like a table, right, and an object standing on a table, and the object is not moving, and there's no horizontal forces, right? There's obviously no friction. That makes, I hope, makes sense. Right? If we apply a force onto the object from the horizontal direction, the friction will try to prevent the object from moving. And obviously, the more force you apply onto the object, the greater the friction becomes. Now, if the object doesn't move, right, that means that the friction force from the object is increasing, right, as we apply force onto it, up until a point where the friction force obviously gets to its maximum value, and then the object goes. Right? So if you have a look on page 83, now unfortunately we're not in the classroom because otherwise it would have been fun to do this experiment, but I'd like you to just in your own time read through that. Okay? It'll give you a better sense of what forces affect friction, right? And the big takeaway from that is this over here, right? A lot of the times people would assume that the weight of the object is what affects friction, right? Because something's heavier, it must therefore have greater friction, right? But with a simple experiment like that one, what you can also do is you can go into YouTube and just Google that spring balance friction test and watch a couple of videos. I'm sure there's plenty of them online that you can watch, and it'll give you a good sense of why the mass of the object doesn't affect friction, but the normal contact force. And the normal contact force is that force that the surface the object is lying on pushes up against the object. Okay? And our friction force is affected by that contact force. Right? So for the remainder of this chapter, right, we need to just look at some variables that we're going to be throwing around. Okay? We're going to call friction F, right, and we're going to call the normal contact force R. And that's the reason I say there's the normal contact force is because we're going to learn about the total contact force as well later on. So friction obviously takes, well, how friction is calculated depends on the two surfaces that are in contact with each other. If we have a rough surface, so two rough surfaces, we will have some kind of friction. And if we have a smooth surface, so we call a surface smooth in terms of motion, that means that there is no friction between the two surfaces. Right, so let's have a look at some simple examples of friction in action. So if we have a look at the first table here, so I've got a table with an object on it. Right, vertically we'll always have forces, right? We will always have the weight of the object acting down, and we have this contact force, which we're going to call R, from the table. So the table is pushing up against the object on the table. And because this is not moving, these two forces must be exactly the same. Now, because we don't have any horizontal forces, there's no friction. So let's move on to the next table in the middle. Okay? We still have the weight of the object and we still have the contact force from this table pushing up, or the surface pushing up if you don't want to use a table in an object. Okay? I've represented with my arrows there. I'm going to say that we have this force pushing on the object. Now, I know in a force diagram, we don't display forces pushing against objects. We normally have the arrows going in opposite direction, but just for the purposes of illustration, just bear with that, okay? So we have this blue force over here, and we have a friction force in red on the other direction, okay? Now, the amount of friction that's generated, right, is something we're going to look at in a second, but if the object remains in equilibrium, in other words, there's no change in acceleration, right, friction can actually increase, right? So remember, for an object to remain in equilibrium, the forces must be zero. So that brings up a very interesting concept with friction, is that I can increase the size of the force on the object, and I'm sure you've pushed something heavy enough in your life to know that sometimes you just can't push it hard enough, because what happens is, as you apply more force, the friction force increases. And so friction can increase to prevent motion, right? So the more force you apply, the more friction force there is. Now, this comes down to many factors which we will look at in a minute. Right? So just in your mind, just think you're trying to push imagine yourself trying to push a car, right? You're pushing the car, but the friction generated by the road surface is, as you're pushing harder, the friction is pushing back in the opposite direction to you, right? As you're applying more force, the friction force is increasing, so the object is remaining in equilibrium, and that's why it's not moving. Now, if you get some of your buddies to come and help you to push the car, so on my last little diagram here, I've now obviously put the friction forces in the correct orientation. This is how you would represent them. So this is the direction we are pushing the object, and this is the force of friction pushing back in the opposite direction. Okay? We can get the object to a point that it's on the verge of motion. In other words, we're pushing it with just enough force that if I push with even the slightest amount more force, the object will move. Okay? We call this the limiting equilibrium. Okay? It's the point at which the object is on the verge of moving, right? So even the slightest bit of extra force would cause it to move. This point is also when our friction is at its maximum value, right? So friction can increase up into a point, but even friction has a maximum value. So if you apply a force just greater than its maximum value, the object will move in that direction. Okay? And we call it, like I said, this is the point of limiting equilibrium. Right? So let's have a look at some of the values, okay, that contribute to friction. So there's two factors that, the values that friction depends on, right? The first of those is the contact force between them. Right? So the contact force that we have been talking about is the force that the surface exerts on the object. Right? I've got it in vertical and at the moment, but remember, objects can be at slopes as well. And the contact force is always perpendicular to the surface. Right, the second factor that affects friction is how rough the surfaces are. Okay, now every surface in the world, right, has a varying degree of roughness, right? And so we have to have some kind of coefficient of friction. So here we have the symbol for friction. And Zara, I did my homework yesterday. That is the Greek letter mu, right? So we use the Greek letter mu as the coefficient of friction, just to give you some where it comes from. And obviously every type of surface in the world would have a different coefficient of friction. Maybe some have been calculated, right? Others can be calculated. And one important thing to remember, if you have a coefficient of 0, in other words, there's no coefficient of friction, that means that we have a smooth surface and there is no friction. Right, so to give ourselves some formula, we've spoken about this middle object, this middle box, or this middle scenario here. And we said, as we are applying a greater force on the object, the friction force is increasing. Okay? But the friction force oopsie, sorry. Okay. So the friction is just a product of the coefficient of friction and the normal contact force, right? That is how we calculate friction. And in the middle there, if the friction force is increasing, right, it's always still going to be less than the maximum value, right, if the object is not in motion. Right? So this part here, this is how we calculate the maximum value of friction. We take the friction coefficient and we multiply it by the contact force, the normal contact force. And just to end off with that, right? The maximum amount of friction that an object can have is also called its limiting, or the limiting value, right? Same thing, limiting equilibrium. It's on the limit. And obviously anything more than that and the object will move relative to the surface. So a lot of new words and mouthful there. Everybody happy and on the same page. We're good with that.
Yeah.
Yeah. You guys look at friction in physics as well.
Yep. We did.
Okay, so just a simple concept, right? Just reminding yourselves, if we go back to Newton's second law or Newton's first law, right? If an object remains at constant velocity or stationary, right, its net resultant force must remain 0, right? And you need to remember that if you push an object, right, it might not move, and you might push it a little bit harder and it might not move. So why is the object not moving, right? Friction must be changing, right? The frictional force must be changing to match the force that you're applying, because if it didn't, then the object should move, right? And if friction was constant, that would mean that when you pushed on it and the friction force pushed against you, the object should actually come back towards you, right? Which is obviously not a good thing for you. You push a car and it comes back towards you, or a building and it comes back towards you. Okay, so that tells us that friction changes as we apply more force to it, right? But there's a limit to the amount of friction that an object can have. We call that the maximum value, right? Okay, let's talk about total contact force. Okay. So we've just seen that we get the friction force from the normal contact force. The normal contact force is the force perpendicular to the surface. Right? So on a flat surface, that's straight up. If it was on a hill, it would be perpendicular to the slope, right? So I can actually just go down. If we have a look at the bottom over there, the R, that's my normal contact force. You can see it's not vertical anymore, but it's perpendicular to the surface. Right, so because the normal contact force and the friction force usually work together, right? We can find out what the total of this force is. Right? The total of these forces is what we call the total contact force. So let's consider how these forces are applied. Okay, the normal contact force is always perpendicular to the surface, and the friction force is always parallel to the direction that the object is moving. And that obviously means that these two forces act at 90 degrees to each other. They're perpendicular. And we've learned in the last lecture or the last lesson that if we have two forces, right, and we want to find the result of those two forces, we can put the vectors end to end, and we can find the force that they are, or that combines them, right? So if I take my friction force and I take my resultant force or my normal contact force, we can join the vectors end to end, and we can find the resultant of that, right? And this resultant force is what we call the total contact force, right? The total amount of force that is generated by the surface that the object is resting on. Okay, so the object is being pushed up by the table or the surface, right? And the surface is also generating a friction force. So if we want to find out the total force that the surface is applying onto an object, we can find the result of the two forces. Right, well, I told you that these two act perpendicular. That's lovely because now we can use good old Pythagoras. We call this total contact force will usually be denoted as C. So if we want to find the contact force, right, it's the hypotenuse. So we can use Pythagoras, and similar to resolving vertically and horizontally, we can take the vertical component squared and add the horizontal component squared. And if we take the square root of that, we can find the contact force, right? The total contact force. So we must distinguish between the total contact force and the normal contact force. Let's see here, the normal contact force, that's the force pushing up perpendicular to the surface on the object. The total contact force, well, that's the result of your normal contact force and the friction generated by the surface. Right, sometimes we'd also want to find the resultant angle. Right? So what angle is this total contact force acting, right? And usually we want to find this in relation to the normal contact force, right? So if I leave my triangle the way it is, this, this angle inside here, which we can call theta for now, that angle inside there is not giving me, it's not going to give me, if I take the tan, right? Remember, tan is opposite over adjacent. So the tan inverse of that would not give me the angle in relation to the contact force. It would give me the angle in relation to the friction force. And so what we can do is we can just shuffle around the vectors. They're still end to end. I still have my vectors one going to the other. Except the difference now is this is the angle that I'm interested in, right? Because this angle is the angle in relation to the normal contact force. We still have a right angle triangle, except now the friction force is on the opposite side and the resultant force or the normal contact force is on the adjacent side. So tan theta would be equal to F over R. And if I want to find the size of the angle, if we call the angle theta, you can call it whatever you want. That would be tan inverse of F over R. So if they asked you, please give the angle of the total contact force from the resultant force, then that's how you would calculate it. Okay, we all happy with total contact force? Understand what it is?
Yeah.
Yeah.
Toya, you happy with that?
Yeah.
Yeah, lots of new forces to learn about, unfortunately, but that's just the way it is, right? And they all work off the same principle, right? The fact that when we combine vectors, we can find the result if the forces are perpendicular to each other. Okay, let's move on. Right, we'll get all the theory out and we can spend the next lesson just going over some examples. Okay, let's talk about making assumptions about friction and the significance of getting negative values, right? So like with Dominic, with her question from the homework yesterday, getting the negative number, sometimes you're like, why am I getting a negative number, right? And the reason you might sometimes get negative numbers that you're not wanting is because you've made the wrong assumption. Okay? So a lot of the time we get information and we don't have enough information to make an accurate assumption, right? And so we make an assumption and our assumption might be wrong. So I want you to consider the object over here, right? We have a box or we have something on a slope. We have a force applying up the line of greatest slope, and we have a friction force, right? So have a look at the two different scenarios, right? The force up the hill is exactly the same in both instances. There's some tension pulling whatever the object is up the hill. Now let's consider the two different scenarios that the friction is acting on. Okay? If we consider the example on the left, in this case, we could say that the tension, right, the pulling force up the hill is greater or is great enough that the object is in motion, all right? And so this friction force, if you want to, you know, what we could do is we could actually, oops, sorry, let's move this guy. If you imagine this thing being dragged up the hill, as you're dragging it up the hill, the friction generated from the surface is actually preventing it from going up. There's some force against the direction of motion, right? And obviously we draw those out in the front, okay? So down over here. So this is the object is moving, it's going up the hill, and the surface is generating some friction. So, you know, imagine pushing a heavy box up a hill, right? The ground is going to create some friction. It's going to be difficult to push the box up the hill. Right, so let's consider the scenario on the right. Okay. In the scenario on the right, imagine that we don't have a lot of tension, right? There's not a lot of force pulling the box up the hill. In other words, the object is actually at the point of moving down the hill. So imagine yourself, you know, you're trying to hold the car by a rope. It's about to slide down the hill, right? And you're holding on for dear life to keep the car from rolling backwards, but it wants to go backwards, right? Well, because the object wants to go down the hill, remember, friction acts in the opposite direction of motion. So what's happening is the friction is actually pushing up against the car, right? In the opposite direction, or with the direction of tension this time. In other words, the friction is actually helping you to hold the car or the object in that position. Now, these are assumptions that we make, right? We don't know. If I tell you that there's tension holding this car in place, is it tension because you've got enough tension to pull the car? Is the friction acting against you? Or is the friction working with you to keep the car in equilibrium? And depending on the assumption that you've made, you are expecting to get a certain value out, right? And usually that's a positive value. But if you assume wrong, you might get a negative value. And the negative value doesn't mean that you've done something wrong. The negative value just means the friction is acting in the opposite direction than you assumed. Right? It still has the same magnitude, it's just acting in the opposite direction. So if we go back to our example here, imagine you assume there's enough tension, right? We're pulling the object up the hill. If we're pulling the object up the hill, then the friction must be acting against us. But you might do your calculation and realize that actually the tension was not enough to pull the object up the hill, and the friction was actually preventing the object from moving down the hill. Okay, does that make sense to you guys? Friction, right? Very important. Yeah. It acts in the direction to prevent motion, and if the motion tends to want to go down the hill because there's not enough tension, if the object is in equilibrium, that must mean that the force of friction must be pushing up against or in the against the direction of motion.
Mr. James.
Yes.
So how do we know which assumption is correct? Right.
When we do an example, I'm going to show you how you'll work it out. Okay. Okay. So we're going to run out of time. So when we run out of time, you can come log back in at 1:15. I'll give you 5 minutes to go to the bathroom quickly. Right. Just before we go, one simple thing to remember is that there is a limit to friction. And so if the friction that you're given is greater than the maximum amount of friction that the object can generate, then obviously the object can't be in equilibrium. Okay. Right, so a lot of new little concepts that we've learned. Okay. Hopefully when we do some examples in the next lesson, so in 5 minutes time, it will make a little bit more sense. And Zara, then I'll be able to answer your question rather with an example that you can physically see what's happening rather than trying to explain what's going to happen.